You'd think with all the chatter going on about climate that we'd all have a good understanding of the elements of our atmosphere, the role of CO2 and other greenhouse gases, and the correlation between human activity and climate change. If you consider yourself to be informed, now quickly, without looking it up, what is the number one greenhouse gas? If you answered water vapor, you'd be right. It accounts for 80% of total greenhouse gas mass and 90% of volume. What about CO2? What percentage is it in the total mix of greenhouse gases? And if you know that, what about anthropogenically generated CO2? What percentage does it account for? Then, what is the dynamic interplay between CO2 within the troposphere, that's where we live, and in the stratosphere, which is a couple layers above us? Why does CO2 heat the Earth in one atmospheric layer and cool it in another? Then there's the sun, which is hot, as much as 17 million degrees at its hottest at the core, and 5,800 degrees Celsius at the photosphere or on the surface. Add in solar magnetic energy and coronal mass eruptions, and the climate equation starts to become very challenging to understand. Now the Canadian government is declaring that we're in an emergency state when it comes to climate. So we sat down with climate professor Simon Donner for a conversation that matters about the science of climate, how it works, what we can individually do to make a difference, and the reality of our climate now and what it looks like as we go into the future.
Conversations That Matter is a partner program for the Centre for Dialogue at Simon Fraser University. The production of this program is made possible thanks to the support of the following and viewers like you.
Welcome. Thanks for joining me on Conversations here. This is another one of the pieces that I'm doing about climate because I'm so fascinated by it. When we take a look at the science of, climate, it is so complex. What are the elements that go into you being able to say, yeah, these are the elements and this is the interplay and this is how we know we're being impacted?
So, it really goes back to pretty fundamental physics and chemistry. And people like myself who teach about climate change, do research on climate change at universities, have training in the physics and chemistry of the climate system. My PhD is in atmosphere and ocean sciences, and it was a lot of physics and a little bit of chemistry.
And it's complex, isn't it?
It's complex, except that it's not this new branch of science. And I think that's where people sometimes get misled, is this idea that scientists, came up with this totally other way of looking at the planet, and Al Gore signed on, and then that's how we came to this. But modern climate science is simply an outgrowth of physics and chemistry. And so, for example, the focus on greenhouse gases, which we are highly confident is the really only cause of warming in the warming of the atmosphere. Right, and the warming of the planet. That comes from from long years of science, experiments that were started in the 1800s, looking at the radiative properties of those gases, how they work, how they're different than other gases in the atmosphere, et cetera.
And was that an attempt to just understand how atmosphere works, and then you start to put it together, and then it starts to grow from a basic understanding of this is the world in which we live in, and we're trying to understand it.
Right, and that's true, and it's really important to understand that the core understanding of the climate and the fact that climate change is being caused by human activity, being caused by greenhouse gases, are being added to the atmosphere by burning fossil fuels and clearing forests. That sounds like something an environmentalist would say. And you do hear environmentalists saying it, but that doesn't mean that it's not grounded in basic science. So the people who did the initial research on how greenhouse gases work, their effect on the atmosphere, how the climate works, and all this stuff, they were just doing what scientists do, trying to understand the planet. And I can tell you, myself, I'm somebody that was just interested in the climate. I was interested in a little bit in ecology. I was interested in the environment and the physics of things. I wasn't looking to become an activist on anything. I was good at math and physics. That's how you get into doing this. It just turned out that the thing I was studying is a majorly important political human issue,
yes,
right?
It is.
I did not, my intention was never to move into that world. I was good at math and physics.
Surprise.
But this is what the math and physics tells us.
Right.
And I'm not, when scientists say climate change is caused by human activity, they're not telling you that they like that or that other people have to like it. They're just telling you this is the accumulation of 200 years of work. That this is what we've realized.
So what is it that carbon does when it's in the atmosphere that traps extra heat within, the atmosphere of the Earth. And there's many people who say, well, that's what makes Earth habitable because it is warmed. I believe it's about, 20 some odd degrees that it's warmed from what it would be if we didn't have the atmosphere.
No, that's right. So if there was no carbon dioxide, if there were no greenhouse gases in the atmosphere, if we didn't have an atmosphere that trapped some of that outgoing radiation from the planet's surface, the planet would be 33, 35 degrees colder. There'd probably be no life on the surface. It'd be a frozen ball, right? And so greenhouse gases allow us to exist, but the more you add to the atmosphere, the warmer the planet's going to get. And it actually really, again, just goes down to some really fundamental physics and chemistry. And so it's about the shape of the molecules. So carbon dioxide, it's carbon and 2 oxygens. The oxygens are sticking out on the side from the carbon. And individual elements have electricity and magnetism to them, which means that the oxygens can get attracted towards each other and then repelled again. Just the way that as you push two magnets together, they start to come apart, right? So imagine that that's happening within the molecule. Now, these are 3-dimensional molecules, so it happens in multiple dimensions. And so you have certain molecules, just based on the elements that are in them, vibrate and rotate in particular ways. And so it depends on the shape of the molecule. So, for example, nitrogen, which makes up 78% of the atmosphere, two nitrogens bonded together, it's symmetrical. It doesn't rotate or vibrate, so it doesn't absorb energy that passes through. But carbon dioxide, because of the way it vibrates and rotates, can interact with radiation that's moving, that has basically a similar frequency. And so it just turns out, it's just the physics of the universe, it just turns out that carbon dioxide is able to absorb a certain type of electromagnetic radiation, which we call infrared radiation or terrestrial radiation, the stuff that comes up from the Earth. It doesn't absorb energy that comes in from the sun because it's a different type of energy.
Because when it's coming in one way, it has a different structure than when it reflects back out.
Right, and so energy moves in waves, and so it has different wavelengths. The sun's energy has shorter wavelengths, the Earth's energy has longer wavelengths. So there are gases that can absorb the Earth's energy and not the sun's energy. And so that's why, and it's incredible because if we look at it, CO2 is not a major contributor to the atmosphere. It's a very small percentage
3%
of air
or something, isn't it?
But if you look at the gases that are higher concentrations, nitrogen, oxygen, argon, they don't absorb terrestrial radiation from the Earth. So that means that carbon dioxide becomes incredibly important because it's doing something other gases can't. It's not the only one, of course. Right. Water vapor, methane, et cetera, also greenhouse gases.
But methane is a form of carbon, isn't it?
Right. So methane is a molecule that includes a carbon in it, but also 4 hydrogen. So it's a different compound than carbon dioxide. And methane actually, pound for pound, is a more effective greenhouse gas than CO2, but there's so much less of it. Yeah, in retaining heat, but there's so much less of it in the atmosphere that it's not contributing as much.
A shorter lifespan as well, a shorter half-life.
It does, that's right.
In the atmosphere. So yes, it may be denser, there's less of it, but it doesn't stay around as long as carbon.
And so one of the things that's really important to understand is that when we burn fossil fuels, you're taking carbon in one form and converting it to another form, adding the oxygens from the atmosphere, creating CO2, putting it in the atmosphere. Now, CO2 doesn't...
The opposite of what happened when a plant or a tree takes it in.
Exactly. It's the opposite formula. So when you add CO2 to the atmosphere, it doesn't stay there forever. In fact, only a little over half of what we emit stays in the atmosphere. The other half gets taken up by land plants, and plants are basically doing more photosynthesis than they would have before. Or some of it is absorbed by the ocean, which causes what we call ocean acidification.
And that's the next part that I want to get to. Yes.
But I do want to say that, so not all of it stays in the atmosphere. But what matters is that more than half that does is going to contribute to warming. And that stays there for a long time. In order for all this additional carbon we've added to the atmosphere from fossil fuels to get out of the atmosphere through natural processes, that's going to take tens to hundreds of thousands of years. Because if you think about it, we've taken carbon that was buried in oil fields, coal fields, whatever, that took hundreds of thousands, in some cases millions of years to be generated naturally, right? And then we take it, you extract carbon from an oil well, in oil from an oil well, you refine it, everything, get it to the vehicle uses it as gasoline. That takes about 3 years. So we have sped up a process that should be taking hundreds of thousands of years, so no wonder it's going to collect in the atmosphere because we've created this imbalance. So it's going to take a lot of time for the system to correct it. Why does this matter for us and for political decisions and human decisions? It matters because the decisions we make now are going to have a long-term impact on the atmosphere. If we emit carbon dioxide now, it's going to be warming the planet for a long time.
Got to get you to hang on for a second while we take a quick commercial break. We'll be right back. Conversations That Matter is brought to you by Odlum Brown, a client-focused investment firm that starts client relationships with straightforward conversations focused on you, your aspirations, and your investment priorities. Odlum Brown has been a supporter of Conversations That Matter from the day we started this show. Their only condition was that we provide a non-biased conversation with people from all sides of all sorts of issues. And of course, we couldn't produce this show without the support of Oh Boy Productions. If you're looking to produce a show like this one, I suggest you reach out to Oh Boy. They can help you produce it, and they can help you build your audience. And we also need your support. I ask you to please pledge $1 per show by going to conversationsthatmatter.tv/donate, because those dollars add up and play an important role in helping us produce this show. Now, back to the show. That brings up an interesting point. I will hear people say, well, the amount of carbon within the envelope of the Earth hasn't changed. It was in the atmosphere before, it got sequestered, became carbonaceous rock or oil and coal and so on. Yeah. And now we're just putting it back out into the atmosphere. But the thing I think that is important to understand here is the speed at which it's returning back into the atmosphere. Why is that so important? As in the way that I guess the rest of Mother Nature interacts with that rapid change.
Well, I mean, you just think of it like all of us have email inboxes that are often overflowing, right? What's going on is the flow in is more than you can process, right?
Yes.
And so that's what's happening here. There's a natural rate at which carbon dioxide moves into the atmosphere, comes back out of the atmosphere over geological time through volcanoes and weathering of rocks on land. And when you can take a geochemistry class at UBC and we'll review all of this for you.
Tens of thousands to hundreds of thousands of years. Yeah.
But there's a natural process, but it's a very slow geological process, right?
Yes.
But what we've done is we're disrupting that process because we're taking carbon out of one of these long-term reservoirs where normally it should take a very long time for it to escape. We're extracting it and putting it into the atmosphere quickly. So the atmosphere doesn't have the capability to or the planet doesn't have the capability to quickly absorb that extra carbon out of the atmosphere, so it's going to stay there for a long time. Not all of it. Some of it comes out, as we mentioned, into the ocean, into land. But somewhere between about 15 and 40% of the CO2 we emit will still be there in 10,000 years in the atmosphere. So you think of the legacy of the decisions we make today, right? Where decisions we make today about, what type of, where we're going to get our energy, where we're going to get our fuel, those are going to affect the climate for really thousands to tens of thousands of years.
Okay, so I'm in an intersection here where I can go one way or another, but I want to get to oceans first of all, because I had Scott Donnie in here a couple of years ago from Woods Hole, and he said, okay, the ocean is a huge carbon sink. Like, it sucks up a tremendous amount of carbon, but it's having an impact on ocean temperatures, the chemical composition, and it's changing behavior in the ocean. And it comes back to that same point that you said, it's the rate of change that doesn't allow the organisms that are at work in the ocean to adapt fast enough. Is that a good sort of recap?
So it's actually interesting in the scientific community, particularly people like Scott Doney that do work on ocean acidification. They use the term buffering or buffer capacity a lot, which you can imagine using just in your daily life. Like, I need to put more of a buffer in so that I have enough time to finish my activities or whatever I have planned for the day.
Yeah.
And so there's a buffering capacity of the ocean of how much carbon dioxide it can take up and what effect that's going to have on the chemistry. And the chemistry here gets a little bit complicated, but the basic idea is that as you add more CO2 to the atmosphere and the surface of the ocean are in equilibrium, so that because CO2 can dissolve in water, if there's more CO2 in the atmosphere, a higher concentration in the atmosphere than there is in the water that it's touching, some of it's going to dissolve into water, and vice versa, right? So that's how we make carbonated beverages, right? So if you have one of those home seltzer machines, you have a canister of CO2, the machine opens the canister and exposes the water to this high concentration CO2 air, and so some of that CO2 goes into the water. You seal the bottle quickly, and it stays dissolved. But as soon as you open up that bottle, now you've got a water with more CO2 in it than air, and it's going to bubble out, right?
Yeah.
And so what we're doing, we're basically carbonating the ocean, right? By adding CO2 to the atmosphere, we're putting more CO2 in the ocean. And once it's in there, it affects a variety of different carbon compounds, basically, which influence all the organisms that use, that build the skeletons out of what scientists call calcium carbonate, which also could be known as limestone, or just what we make our bones out of. And so organisms like tropical corals that build reefs out of basically bone, the ability of corals to do that gets limited as you put more and more CO2 in the water.
When you take a look at where we're at, our understanding of the science of climate, where we're moving politically and from a societal perspective, do you look forward with hope that we're going to make adjustments in our behavior to, hopefully get on top of this? Because, and I ask that because I don't think that people are going to turn away from energy consumption. And so, is there hope? And if so, then what is it and how do we get there?
No, and it's an important question. I'm actually optimistic. And I think whether people are optimistic or pessimistic sometimes is just about their personality as much about the data. But I'll tell you why I'm optimistic. Most of the things that we need to do to reduce greenhouse gas emissions are good ideas for some other set of reasons.
Yes.
And so there's a lot of reasons we can do that. And we're mostly at this point where it's about political will and it's about mobilization. Like the technologies and the abilities, they all exist basically now.
Yeah.
We could do this. And I'll give you an example. So the activities that are driving fossil fuel emissions, burning coal, driving internal combustion vehicles, et cetera, right? Those are also causes of air pollution. And I don't mean carbon dioxide air pollution. I mean smog and particulate matter, like small little bits of soot that are hard on asthmatics like me, right?
Yes.
And here's the thing, like if we solved climate change, we would solve air pollution. We could eliminate air pollution and, oh, by the way, also solve climate change. Like, so there's all these good reasons to do both. Right now, we have, political systems in Canada and the United States that are struggling with this because of just the dynamics of electoral politics, and the way information's transmitted these days, where we have these sort of alternative universes of facts that are available online that are causing challenges to this. But I mean, I think I'm energized by seeing how much young people are taking over.
I'm happy to hear you say that you're optimistic. My understanding of a great definition of an optimist is somebody who is fully aware of the challenges and pitfalls ahead of us, but chooses to seek out hopefully positive outcomes. I think that it's important that we have that sense of optimism. Otherwise, we might throw up our hands and go, oh, well, what's the point? It's all lost. And that, I think, is a greater risk.
No, and I'm with you on that. And there's some research that shows that, scaring people, scary messages about what's happening to the environment does exactly that. It provides paralysis. Now, that depends on who you're communicating with, of course.
Yeah.
And I don't think optimism that's fake, I don't think is going us anywhere. So I want to be clear about what I'm optimistic about. I'm optimistic that we can reduce greenhouse gas emissions and that I'm optimistic that we are going to shift faster than people probably expect to vehicles that don't run on gasoline. Because I think we're near like kind of a tipping point in the technological change and the people realizing, whoa, I could have an electric vehicle and I could still get to work. And so I think some of these things are going to happen. I'm not optimistic about us doing it fast enough to avoid some of the temperature limits that have been discussed in international policy. So for example, the idea that's been proposed, and I have contributed, some of my research has contributed to this, to saying that more than 1.5 degrees of warming is dangerous for a variety of reasons. I think it's highly unlikely we could avoid that. Like it's not technically impossible, but it's probably logistically impossible at this point to avoid 1.5 degrees, and 2 degrees at the rate we're going is also going to be quite unlikely. Now, those numbers are not numbers that come straight out of physics. Science can't tell you what's dangerous. That's a human decision. But they are things that the world has sort of agreed we want to avoid. And so I'm not optimistic about avoiding those targets, but I do think we'll will be able to get off of slow greenhouse gas emissions.
You have this this sense of optimism, but there are a number of people who are putting out messages that are designed to scare us, and you point out that that doesn't necessarily work. When we look at that, how does it kind of fit into like what we know and the messages that we're getting on the outer edges of the whole discussion around climate?
Well, one of the things I think that's hurt the communication about climate change from the scientific community is just the norms of science, right? And so our expectations for certainty are so much higher than that in the general public. In science, nothing's ever 100% certain. We still call gravity a theory. So when I talk about climate change with students, I always try to drive this point home that there are things we know with incredibly high certainty and things that there's a little bit less certainty about. And it's important to distinguish between the two. If you go out a little bit further, then there are things that we don't know with quite as much certainty. And you might use a term like extremely likely rather than a term like virtually certain. Extremely likely in the scientific parlance means greater than 95% chance. That's still pretty likely.
It's still pretty good.
And then you can go out further still and say things that we think this is more likely than not, but we're not absolutely sure. And that sometimes is, how's the rainfall going to change in my part of the world in the summer? Like something specific like that. Where I think the climate denialist community is really dishonest is they poke a hole at something on the outside and try to use that to claim that the core is wrong.
Okay, so whose responsibility is it to help us change our behavior? Is it ourself, or does it have to come from above? Government regulations forcing industry to change and imposing changes upon us, or is it a combination of all of those things?
Well, the thing with climate change, it's the world's biggest collective action problem, right? I mean, there's no thing we all share and use the most, more than the atmosphere, right?
Right.
And so there's no one solution. There's no silver bullet. It's more of like a silver buckshot. And I think that there's a lot that individuals can do, from the choices you make about the vehicles you drive, what you eat, et cetera, et cetera. But governments need to set the incentives.
Right.
And so I think the thing, especially with, here in Vancouver, in Canada, a lot of Canadians want to make those choices, but they'll say, there aren't enough of those vehicles available where I live, or public transit's not good enough, or whatever. Or, that costs too much and this is too cheap, so I'm going to do this instead. That's where government comes in, where we need the incentives. And so I don't think it's just up to government. Because even if government put the incentives in, people still have to make the decisions, right?
Right.
So we can't just say the government's going to solve this.
Right.
But we need to work together. And right now,
well,
it's not going as well as I'd like.
And I also hope that there are scientists who are doing things. You take a look at carbon engineering, the work that they're doing up in Squamish with carbon sequestering. And I just read about a young woman at the University of Alberta or University of Calgary. She's figured out how to sequester carbon and turn it into other forms of like solid material that can be used. The collective will to get this done, I think, is what can help us get there. I wish I could go on longer. Thank you very much for coming in and
Thanks,
sharing
Derek.
this. This was fantastic.
Thank you.